Hey gang, welcome back to 4600. We're moving on into chapter 7. Some of the elements and theorems that we learned in 6.5 will come up today. I'm going to split this lecture into two separate lectures, and we'll kill out and we won't do section 7.5. Honestly, that section is interesting, but it's not something that is used very often, so we will skip that section. And I'll replace, we'll do a lecture over the first half of this. One day I'll release that, next day I'll release the second half of this, and then I'll go over some homework problems in the third one. And then we'll move on to 7.3, which deals with the central limit theorem. Today we're going to talk about sampling distributions, and it's section 7.2, and it's chock full of all kinds of stuff about the sampling, different versions of the sampling distributions that come from the normal distribution specifically. All right, so to kind of start this off, though, I'm backing up to 7.1 a little bit, which is kind of an introduction to the chapter. And I just want to read this with you because I think it's important. So in this chapter, we will be working with functions of the variables y sub 1 through y sub n observed in a random sample selected from a population of interest. The random variables y sub 1 through y sub n are independent and have the same distribution. Basically, they'll all have the normal distribution to a certain degree. So certain functions of the random variables observed in a sample are used to estimate or make decisions about unknown population parameters, such as the population mean mu, the population variance sigma squared, and the population standard deviation sigma, to name a few. For example, suppose we want to estimate a population mean, right? If we obtain a random sample of n observation, little y sub 1 through y sub n, it seems reasonable that we can estimate mu with the sample mean y bar. And if you've had a class where you've done any kind of confidence interval hypothesis test revolved around the mean, then we used the sample mean to estimate something about the population mean mu. All right. The goodness of this estimate really depends on the behavior of the random variables y sub 1 through y sub n, and the effect that this behavior has on y bar. Okay. So notice that the random variable y bar is a function of only the random variables y sub 1 through y sub n and a constant, which is the sample size n. The random variable y bar is therefore an example of a statistic. And we've gone over statistics before. Basically the definition in the book for a statistic is a statistic is a function of the observable random variables in a sample and known constants. So that's what y bar is. It's made up of y sub i's and the constant n, right? So because all statistics are functions of random variables observed in a sample, all statistics therefore are random variables. All right. Consequently, all statistics have probability distributions, which we will call sampling distributions. All right. If you've had biostats with me before, we did discuss sampling distributions for a minute, but we're going to get a little bit more detailed into it today. And kind of, a little bit more into it than we did before. Okay. So the first example I want to do is more kind of like a precursor to what we do with the sampling distributions. But what I want to do with example 1 is showcase for you a situation where we have samples taken that are, in other words, we're not just pulling one item out of a population. We may be sampling 2 items out of a population in this case. And to see what happens to what we call the sample, the mean of the sample means, and how it's related to the population mean, which is what denoted mu sub y bar, and the standard deviation of the sample means denoted sigma sub y bar, and how it's related back to the population standard deviation. Okay, so that's kind of an important thing we need to at least get a view of. So in this example 1, I'm going to take a balanced 4-sided die. So we've got one of those. We're going to toss it twice, and that's going to be giving us a sample of 2. So we're going to let y sub 1 and y sub 2 denote the number observed on the upper face for tosses 1 and 2 respectively. And suppose we're interested in y bar, which equals y sub 1 plus y sub 2 divided by 2. The average number observed in the sample of 2, or sorry, that sounded like I was reading it weirdly. I did read that weirdly. So basically we want to find out what are the mean of the sample means and the standard deviation of the sample of y bar, or the standard deviation of the sample means, if you will. Okay, so setting this up real quick, and I'll try to go through this as fast as possible. We've got one four-sided die. We've got a four-sided die, and on that die, if you've ever seen one, these are kind of a pyramid-shaped die. It's the numbers 1 through 4. Okay. If we just add those four numbers up and divide by 4, we find that the population mean for this small sample is 2.5. And if we calculate the variance of this guy, we get that the variance, sigma squared, is 1.25. Okay, we won't do the calculations there. And you're probably wondering, why are you using a discrete case to show this? It's easier to use discrete cases to show this kind of example than it is to use continuous ones. So we'll save, most data we do work with are continuous, but we're using a discrete random variable to showcase the same feature. It works either way. Okay. So if we roll the die twice, right? We can get a sample of n equals 2, and we can observe the numbers on each face and then average those numbers together. All right, so the question is, what are the possible values for y bar? All right, that's really the question. So we need to kind of come up with all the outcomes. There are going to be 16 of them because we've got 4, and we're going to choose 2 of those numbers for each sample. So 4 squared is 16. So I'm going to make a little table here so we can calculate the sample means real fast. So I've got my sample. I've got y bar. And so we have enough room here. I'm going to do another sample, column, and y bar. So give us some room here so we can save some space on the slide. All right, y bar. So easily enough, we could start at 1 and we could go, well, we could roll a 1 on the first, a 2 on the second roll, a 1 and then a 3, a 1 and then a 4, and a 1 and a 1. I forgot that one. I usually like to list that one first. 1 and 1, 1 and 2, 1 and 3, 1, 4. Then we could roll a 2, 1, 2, 2, 2, 3, and 2, 4. We'll stop there and move to the other list. 3, 1, 3, 2, 3, 3, and 3, 4. And then finally a 4, 1, 4 and a 1, a 4 and a 2 on each die, a 4 and a 3, and then a 4 and a 4. All right, so we got those. So basically we just need to take those samples, each one of them, and calculate the sample mean for each one. Luckily, these numbers are nice. That's why I picked this example. So we can sum these up pretty quick. So the average of rolling a 1 and a 1 is just going to be 1. The average of rolling a 1 and a 2, that's 3 divided by 2, or 1.5. 1 and 3 should be an average of 2. I'm just going to list these out because I know you guys can average those numbers together. We get 1.5, 2, 2.5, and 3. Then here we get 2, 2.5, 3, 3.5, 2.5, 3, 3.5, and 4. So the possible values are 1 for y bar in this situation are 1, 1.5, 2, 2.5, 3, 3.5, and 4. All right. So if you take the time and you actually add all those together, I know some of them are repeats, but if you need to add them all together because they're all different samples. If you add all those together to compute the mean, the net of the sample means, the mu of y bar is equal to 2.5, which lo and behold is the same thing as the population mean of mu. If you calculate the variance of this guy, and I would probably use technology to do that because there's a lot of numbers there, but sigma squared of the sample means of all those values in the y-bar columns is 0.625. So the question comes, all right, the mean was the same, but the variance has changed when we sampled. So what's the relationship between, so how is sigma squared sub y-bar related to sigma squared? Well, it's pretty straightforward, although it might take a minute to see it. But the sample sizes we took of each one were n equals 2, correct? So we got that. So if you took the population variance and divide it by 2, that equals 1.25, or sorry, not 0.125, 1.25 divided by 2, which equals 0.625. So dividing by the sample size, the original population variance by the sample size, gave us the same thing as the standard deviation of the sample means, sigma squared sub y-bar. So the rule here is thus, when we sample from a population, a normal population, that is, I should state that too. When we sample, when we sample from a normal population, we use sigma squared over n rather than sigma squared. All right. If we took the square root of this, so this is the variance, right? This is sigma squared sub y-bar. But if we took the square root of, then sigma sub y-bar is just sigma over the square root of n. We call this, and I don't know if the book mentions this or not because I didn't take the time to look to see if it did, and I didn't see a specific definition, but we usually refer to this as the standard error. And that's really the value we actually technically use, although they're really the same value in the long run. Just one of them you take the square root of, or the standard deviation you get from taking the square root. So basically, realistically, we use the standard error in place of the standard deviation when we do calculations involving the normal distribution. Okay, so that brings me to the following theorem. It says, let y sub 1 through y sub n be a random sample of size n from a normal distribution with mean of mu and variance sigma squared. Then y bar equals 1 over n times the sum of y sub I is normally distributed with a mean of mu sub y bar equals mu and variance sigma squared sub y bar equals sigma squared over n. Now we can use stuff from if we go back to section 6.5, theorem 6.3 can help us do a little proof of that these things here are true. Okay, so the proof here is just using some it's just really an algebraic proof. So if you've got y bar which equals 1 over n times the sum of I equals 1 to n of y sub I, that's equal to 1 over n times y1 plus plus 1 over n times y sub n, which really turns out to be that 1 over n is just a constant. So we can call 1 over n a sub 1 times y sub 1 plus a sub 2 y sub 2. Now that was one of the criteria that we had to be able to write our function of random variables in such a way if it was normal, right? And so that was kind of the first clause. So mu sub y bar is really equal to the expected value of y bar, which equals the expected value of 1 over n times y1 plus plus 1 over n times y sub n. And if we expand the expected value, knowing that each y sub I variable is normal, because it told us that in the theorem, then we get 1 over n times mu, and every y sub I value is going to be mu if we take the expected value of it. So we get 1 over n plus times mu plus dot 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 plus all the way to the nth term. We get 1 over n times mu there. All right, okay, which is just 1 over n and times n times mu, because it's mu added together n times, which just turns out to be mu. Therefore, mu sub y bar equals mu. Similarly with the variance, sigma squared sub y bar, that's the variance of y bar, which just equals the variance of 1 over n times y sub 1 plus dot 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 plus 1 over n times y sub n. So all the y sub I terms multiplied by 1 over n. And the variance formula, or the variance rule we saw back in chapter 5, says if we pull a constant out, we can square it. So we get 1 over n squared times the variance of y sub I, which will be just sigma squared. They also told us that up here as well. And that happens because this is normal, plus dot 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 plus 1 over n squared times sigma squared, which just equals 1 over n squared, constant, times n times sigma squared, which just equals sigma squared over n. Therefore, that proves that as well. So obviously they're normally distributed because we could write them that way, and that's kind of a little short proof to show that that indeed works out, and they actually equal those values. So that's pretty cool. When we're dealing with the normal distribution, it's been a while since we've done it, and when we did it in chapter 4, we used instead of looking at probabilities and tables, we used our calculators to find them. Find the probabilities, or find the inverse norm, which is the quantile or the percentile value that corresponded to a certain probability. The chapter 7, we're gonna have to get used to using the z-score formula, which we have seen before, but it's been a minute. But the z-score formula under the conditions of 7.1, y is normally distributed with mean of mu sub y bar equals mu and variance of sigma squared sub y bar equals sigma squared over n. It follows that z, which is a normalizing function, in other words z, which we've seen before, will standardize any data value we have when we know the mean and we know the standard deviation, or in this case the variance. We can set that to a nice normal distribution where the mean is 0 and standard deviation is 1. The reason why that exists is so that we can take any data set we're interested in and make things fit on a standard normal curve. Then we can use tables to find probabilities or to find z-scores, which correspond to the percentiles or quantiles of that distribution. So in this case, z equals y bar minus mu sub y bar over sigma squared sub y bar, which just equals y bar minus mu. Just replacing based on this formulas up here, divided by sigma over the square root of n. So in the denominator, we actually simplified it by taking the square root and made the standard deviation, because this is typically how this is drawn right or written right here. Okay. You'll see different variations on this, but it's pretty much a similar concept. The book writes this as the square root of n times y bar minus mu over sigma. Either way is an acceptable way. I'm just so used to this way, I don't worry about rewriting it a different way. So write it the other way if you really just want to. So before we start trying to find probabilities using the z-score and learning tables, I want to go through some of these problems when we go through them, whether we're finding a probability using a z-score, or whether we're finding a quantile or percentile using the z-score. We need to learn to do it a couple of different ways. Good statisticians know multiple ways to find things, and while we have technology at our hands, and I'm going to be okay with you using those things, and I'll show you different methods for that, I'm going to also show you how to use the table, because I don't know how often you've had to use one of the distribution tables, but first time learning them or using them, it's a little bit weird. So we will go through that as well. But a quick note on technology for the normal distribution. So as far as technology is concerned, We've got two methods with this particular distribution that we can deal with. Hopefully my computer doesn't go to sleep on us. It's not supposed to be. Anyway, we can use your TI calculators for a normal distribution. And to find the probabilities, we use normal CDF, which we did back in chapter 4. So if you answer a question using that, you need to do some of the notation prior to using this function. But then you can use the normal CDF, which takes the lower bound, upper bound, then 0 and 1 for the mean and standard deviation here, because we're going to be dealing with a standard normal distribution. That's why we're going to convert things by a z-score and do things kind of the old-fashioned way for this section. Then if you wanted to do the inverse of this, not find a probability, but find the quantile or percentile, then you use the inverse norm function. And you usually, depending on the calculator variation you have, you got to put the area to the left of where the value sits. So if you think about real quick, I'll just kind of draw it out. You got a normal distribution curve, and you're interested in finding this quantile here. You need to put the area corresponding to the left of that in there usually. Some of the newer versions of the calculator, I think, give you center and right options. So if you've got those, that's great, but if you don't, then it's usually area to the left in there, but then it's just 0 and 1 for the mean and standard deviation. With R, which I'm going to do all my examples with R and not the calculator, because R will do all the functionalities that we need, and the calculator only has normal in T for both of these, for both the probability and the quantile finding functions. They do have chi-square probability and F probability distributions, which we'll go over as well, but they only do the probabilities. They don't do the inverse and give you the actual quantile or percentile that you might be interested in finding. So R will do that for us, and I'll show you how to do that in R for technology. So I will stick to the R method. But in R, you can use p-norm, which I think if you took biostats with me, you've used this before. You put in the quantile value or the x value, y value, whatever you want to call it down here. It's understood that it's 0 and 1 if you've standardized the values. Otherwise, you have to put in a different mean and standard deviation. But what this calculates when you just set it in R like this, with a value in place of q, is it finds the probability that y bar, technically, in this case, because we're dealing with y bar, is less than or equal to the q value you plug in. It'll give you that probability. The inverse of that is the quantile function q norm, and you put in the probability you want, usually the probability to the left that you're interested in, and that produces what it does when you just do that. Again, it assumes 0 and 1 is the mean and standard deviation, but it takes and finds the probability that y bar is less than or equal to phi sub p, which equals p. And so what it's actually doing is whatever the probability that the p value you're given that in the problem, and you're finding this value here. So what that'll calculate, it gives you the value where that is that y is less than or equal to. Okay. If you have to find the opposite, there's some other tricks you can do, and we'll probably see that pop up at some point during the lecture. All right, so let's get into an example. Example 2 says a bottling machine can be regulated so that it discharges an average of mu ounces per bottle. So it didn't give us mu, but it has been observed that the amount of fill dispensed by the machine is normally distributed with sigma equal to 1.0 ounces. A sample of n equals 9 filled bottles is randomly selected from the output of the machine on a given day, all bottled with the same machine setting, and the ounces of the fill are measured for each. Find the probability that the sample mean will be within 0.3 ounces of the true mean mu for the chosen machine setting. All right, so we know n equals 9 sample size, and we know sigma equals 1. So that information we have. What they're asking us to find is the probability of the absolute value of y bar minus mu. We want us to find out when that is less than or equal to 0.3, within 0.3, which just equals really negative 0.3 less than or equal to y bar minus mu less than or equal to 0.3. So just branching that out. Okay. Now if we divide everything, what I'd like in the center here is to get that y bar minus mu to become a z stat is what I'm going to call it, a z statistic or a z variable. So what I need to do is divide that by sigma over the square root of n. So this equals the probability of, in the middle I'm going to get y bar minus mu over sigma divided by the square root of n, less than or equal to, less than or equal to. Here I'll get I'm going to do it everywhere, negative 0.3 over sigma divided by the square root of n, and then 0.3 divided by sigma divided by over square root of n over there. Okay, so we've got that. This thing equals, if we plug in the values we have for n and 1, and we're going to do it everywhere but in the center. The center is just going to become z. So we end up getting p of negative 0.3 over 1 divided by the square root of 9. It's less than or equal to z. It's less than or equal to 0.3 over 1 divided by the square root of 9. And that all simplifies to the probability of negative 0.9 less than or equal to z less than or equal to positive 0.9. And we need to figure out what that equals. All right. So basically, in terms of the normal distribution, what is that asking us to find? If we think about the normal distribution, just draw a little sketch here. We're in between. We're centered. The probability is centered between negative 0.9 and 9. So negative 0.9 is probably about right here. Positive 0.9 is probably about right here. And we're interested in finding this area, the probability, the area underneath the curve there. So the first method we've got to go through to figure this out is the table. All right, and the distribution table that's in the back of the textbook. If you've got a digital copy, it's pretty easy to find. You just go to Appendix 3, which is tables, and go to the normal curve areas. And you'll notice here that the way this is set up is to give you the area above the value of interest to the right of the value z-score. Okay. So our z-score was 0.9, so when we find that on this chart, it's going to give us just the area to above that. It won't give us the area to the bottom side of that, but if we go down to the z of 0.9, and it's 0.9 exactly, and then go over to 0.00 column, that's the second, that's representing the second digit, so if it was 0.91, we'd go over to here. But since it's 0.9 exactly, we're going right here. So it tells me that the probability to the right of 0.9, the z-score of 0.9, is 0.1841. So that's 0.1841. But I've also got a negative 0.9, and I need to know the area below that so I can find the area between. The tables are kind of a pain in the butt, to be honest with you, but it's worth knowing that how they work. Because some people still like for you to use them. But because this is symmetric, and I'm going from negative 0.9 to 0.9, say that z represented 0.9 right there, then the areas to the left of negative 0.9 and to the right of 0.9 will be the same value, so they'll both be 0.1841. All right. So technically, I'm looking to get the areas I don't need to get the area I want using this formula. So it's just going to be equal to 1 minus 2 times that area, which was 0.1841. And that gives me a probability of 0.6318. All right, that's using the table. We can use technology to get this. So if you use the TI calculator to do it, and I won't run this, but it's just you just take normal CDF, negative 0.9, sorry, comma 0.9, the lower bound, the upper bound, mean and standard deviation are 0 and 1, and you'll get 0.6319. it rounds off a little differently because you're getting a more exact answer from the technology. In R, you can do the same thing, but this time you have to do P norm of 0.9 minus P norm of negative 0.9, and that should give us the same thing, but we're going to double check it real quick. So what happens, I have R pulled up. I'm going to clear this out. Oh, actually I already did it, but you can see it right there. P norm of 0.9 minus P norm of negative 0.9 gives me 0.6318797, which is good enough to round this to 4 decimal places, which I recommend for all probabilities. 0.6319 we get there as well, and that's pretty sure that's what your TI calculator would spit out for you as well. So it gives us the same answer either way, and that's cool. So again, if you use one of these two technologies, or you use the table in a homework problem, make sure you notate that where you got your value from, and don't just assume I know where you got it from. So if you use normal CDF, you need to write, just like you did back in chapter 4, you need to write this out in its entirety as your answer so I can see what you plugged in. If you use R, just write this out in its entirety. If you use the table, just note I used table 6, I think it was, the normal distribution is table 6. Table 4 is the normal curve. It's table 4 in appendix 3. All right, notate that for me. So let's do another problem associated with this one, which kind of asks a little bit different question. All right, so it says, refer back to example 2. How many observations should be included in the sample if we wish y bar to be within 0.3 ounces of mu with probability of 0.95? So again, now they're giving us a probability they want us to be equal to, and it's the same within 0.3. So everything's pretty much set up the same, with the exception now we know what the probability outcome needs to be, but what we don't know is what n is. N equals what? So that's what we're looking for, the sample size we need so that we can assure that we'll be within 0.3 ounces with a 95% probability. So the same setup goes here. Matter of fact, I'm going to write this over here a little bit, give me some room over there. Probably that y bar, the absolute value of y bar minus mu is less than or equal to 0.3 equals 0.95. Okay, which is the probability of negative 0.3, again less than or equal to y bar minus mu, which is less than or equal to 0.3, which equals, I'm going to write this out real quick, probably a negative 0.3 over 1 divided by square root of n, less than or equal to y bar minus mu over sigma over the square root of n, is less than or equal to 0.3 over 1 divided by square root of n. And I will say that it's important that you write things out like this in this section, because this is prop stat 2 and not elementary statistics. Use the notation, because if you don't, that's something that'll get you burned on the homework. So make sure you use the notation correctly. That's something I'll be picky about. And if I clean this up real quick, it just gives me the probability of negative 0.3 times the square root of n, which is less than or equal to z, which is less than or equal to 0.3 square root of n. And that is supposed to be equal to 0.95. So that's about as far as I can take that without figuring out what in the heck n has to be. Well, how do we do that? Well, first of all, we kind of need to know what the z-scores are that contain a 95% interval of this in the center of the distribution. That is, what we need to know is if this represents 0.95, we need to know what x1 and x2 here are. Okay. One way to do that is to take and use inverse norm or the Q norm function in R, which is what I'm going to do. But notice that if it's 0.95 in the middle, you got 5% left over contained in your tails combined. So here you got 0.025 area underneath the curve past x of 2, and below x of 1 you've got the same amount. That will help you out in the long run. I'm going to clear this out real quick, because what I want to do there is I technically want to use Q norm, and I don't need to do this for both because of the symmetry of this curve. When we have a standardized curve, normal curve, it's symmetric. So if I can find x2, I'll know what x1 is because it'll just be the negative version of x2, and vice versa. So if I find the x2 value, I'm going to plug in 0.95 plus 0.025, which is 0.975. And if I plug that in, and it automatically assumes 0 and 1, it tells me that value rounded to 2 decimal places is 1.96. And I would assume that if I recall Q norm and then put in just 0.025 below that x1 value, this will give me the x1 value. It gives me negative 1.96, and it does. So the symmetry works out, and symmetry is a beautiful thing. So the way I did that was I said, well, x1 equals Q norm. And again, you don't have to show both, as long as you, with normal you don't have to show both. Some other distributions you do. But Q norm of, what did I do, 0.025, which gave me negative 1.96, and the next two was Q norm of 0.975, just adding the areas below x2, and that gave me positive 1.96. So it turns out that the probability equals 0.95 when we're between negative 1.96, when z is between that and positive 1.96. All right. And so to figure out what n is, we just need to take, it doesn't matter which n we take, it's going to give me the same regardless. I need to take that and set it equal to this and solve for n. So if I do that, then I get 0.3 square root of n equal to 1.96. I solve that for n. I should get n equals 1.96 over 0.3 quantity squared, which just equals 42.68. But we don't want to answer a question like this with a decimal value. You can't sample 42.68 items, in this case filled bottles. You can't sample a portion of a bottle. It's either you take the whole bottle or you don't. So it'd be silly to do that. So always, no matter what the decimal value is, it could be 42.001, 42.42, 42.9999. You always round this value up. Always round up to the next whole number. All right. So the answer technically is going to be 43 samples are needed. So n equals 43. Now, in this case, since it was bottles, I guess, was it machines? Yeah. Sample, where did it say that? Randomly filled bottles are randomly selected. So yeah, filled bottles. So that's what it is. So it's not just samples; it's filled bottles. Again, the units. When we know what the units are, we include them always. All right. So that's it to that. Not too bad, right? This is probably a lot easier than chapter 5 so far. So the next thing we're going to get into is a little bit of what we call the chi-square distribution. And you guys are a little bit familiar with the chi-square distribution, especially if you took either Dr. Trimboli for one of the applied stats classes. You've probably done something with chi-squared, or if you took me for biostats, you've definitely done something with chi-squared. But we're going to discuss two different ones. Today we'll discuss one, and the next lecture we'll discuss a slightly different variation of it. But in the succeeding chapters, we'll be interested in statistics that are functions of the squares of the observations in a random sample from a normal population. So if we took that z, z normal distribution, z formula for standard normal distribution, and we square it, we all of a sudden get a chi-square distribution. We kind of saw that in chapter 6, right? 6.5, we kind of did something with that as well. And so if we sum up the z sub I squareds, all the squared z terms, from 1 to n, it's equivalent to summing y sub I minus mu over sigma n times, all right, squared, quantity squared. And it'll have a chi-square, this will have a chi-square distribution with n degrees of freedom. All right, this is not the typical chi-square distribution we're used to. The one we work with next will be the one that's kind of more broadly used, but this one is to deal with z sub I squared terms specifically. So pay attention to if they ask for this, or if they could do something in terms of this, that it tells you that you're using this one. So one of the things I want to note here, and I'll kind of put a little bit more information in the next slide on this, when using tables, because the only way you can find the quantiles or percentiles of the chi-square distribution is either with technology or with the tables. And with technology you can only use R, which is why I'm only doing R, or the tables. So I will show you both methods. But when using the tables to find probabilities and quantiles, the alpha value is very meaningful, or the probability value the alpha represents. So the probability that x squared, or chi squared, is greater than chi squared sub alpha is equal to alpha. So notice the greater than symbol here. Okay, that's important. It implies that the inverse, or if we flip around this, the greater than symbol and become less than or equal to, or chi squared is less than or equal to chi squared sub alpha, that alpha also all of a sudden represents 1 minus alpha. So whenever you see a less than or equal to in this direction, the probability over here is representative of 1 minus alpha. All right, so that probability is equal to 1 minus alpha. And to find alpha, you got to do 1 minus the probability, essentially. So, and what that 1 minus alpha represents for us is the area to the left, where alpha is the area to the right, if you think about the curve. And you'll see that in just a second. Area to left, area to the right. It's important to know that. Very important. And so the chi-squared sub alpha is equal to phi of 1 minus alpha, or the phi is what we're using to represent a quantile or percentile. Phi sub 1 minus alpha. All right, so the alpha value is just alpha. But if we're doing the less than case here, then 1 minus alpha is the actual quantile value. So that will represent the 1 minus alpha quantile of the chi-squared random variable. So we're going to have to find those, and it's important that we make that distinction. Similarly, we'll see the same trend with both the t-distribution. Technically, the normal distribution has the same scenario going on as well, but then also the F distribution, which we'll talk about next class, will also have this same feature. So this implies to more than just this distribution. All right. So looking at this graph right here, this is your 1 minus alpha, all right? And the chi-squared sub alpha this is your alpha value. So this was where the probability of chi squared was greater than chi squared sub alpha, which equals alpha. And then if you found the area in white over here, that would be the probability that chi squared is less than or equal to chi squared sub alpha, which is just another way of saying the quantile value, would equal 1 minus alpha. So that's what that's saying there. So that's that information in a nutshell. Let's take that off there because I don't really want that there right now. All right. But what I want to do, though, is that this represents the 1 minus alpha quantile or percentile. I'm going to write percentile. You'll notice that they use the word percentile and quantile interchangeably in this section. So if they ask you about quantile or percentile, it's the same thing. Okay. But for the chi-square distribution, no matter which type we're doing, the TI does have a chi-squared CDF function, so it'll find probabilities. And it usually takes a lower bound an upper bound, and then it asks for the degrees of freedom. But that's all it will do. All right, so this will find probabilities. In R, you can do both the probability function and the inverse, and it's called p chi-square, or p chi-sq. And so within that, you throw in the q value, or technically the chi-squares of alpha value that you're interested in, and then the degrees of freedom will come next, and this will calculate for you the probability that y bar, or not y bar in this case, just y, is less than or equal to the q value that you've plugged in. All right, so that'll give you the probability. To find the quantile or percentile, you use q chi-square. That's what I love about our same function, but just with a different beginning letter. Here you're plugging your probability area to the left or right. You can plug in the right. You just have to set an extra setting in there to make it give you the correct area. But this will calculate the probability that y is less than or equal to phi sub p, which equals p. And again, what the q chi-squares calculates for you is that particular percentile or quantile that fits in, that makes this statement true based on the probability given. Okay. And then the book has Appendix 3. In Appendix 3 has Table 6, which we'll use, and I'll show you how to use that in just a minute. So this is a good example here, and this is where we'll stop for today. But we'll go ahead and finish this one out and be done. So if I've got z sub 1 through z sub 6, and it denotes a random sample from the standard normal distribution, they want us to find a number b such that probability of the sum of the z sub I squareds from 1 to 6 is less than or equal to b, and that probability equals 0.95. Okay, so we're going to use the table to find this value. We don't really need to write much out here at the beginning because it's kind of set up for us. But using the table, I know a little bit of information. I know that the degrees of freedom are equal to 6 here. I also know that this is 1 minus alpha. Therefore, alpha equals 0.05. This is important here, folks, when you're using the table, because the way this table, the T distribution table and the F tables work are based on you knowing what alpha actually is. It works off of alpha, not 1 minus alpha. So to find the correct value, we need to know that. Okay. So using the table, we're going to look at the row headed 6 and column chi-squared sub 0.05. All right, and we'll see the number. Let's go to that table. So we're looking for chi-squared sub 0.05 and degrees of freedom 6. Note that though we didn't have to subtract 1 from this like in other degrees of freedoms, because this is a z sub I squared and it said that it was in degrees of freedom. So going down here to table 6, you'll notice across the top here it gives the chi-squared sub alpha values. So it starts at 0.995 and then goes down from there. So we need to go to the second page because it will have the chi-squared sub 0.05. There's a page down here. So chi-squared sub 0.05 is right here. We go down to the 6th row of degrees of freedom right here and come across, and we get 12.5916. I'll write that down, then I'll switch us back over. All right, so that information we have. We basically answered the question in a nutshell. All right, and so the probability that the sum of I equals 1 to n, or to 6 in this case, of z sub I squared is less than or equal to 12.5916. 0.5916 is actually equal to 0.95. So there's our answer technically. All right, that's the true answer. But we can use R to find this real quick. If we use R to find that value, we're going to use the q chi-square function. So in R, if we do q chi-square, and remember this finds the area below, so it's less than or equal to, we don't have to worry about the alpha value in this case. But if we plug in 0.95 and then degrees of freedom of 6, it should give us the same value. Let's double check that. We got q chi-square of 0.95 comma 6, and it does. It gives me 12.5916. Actually a little bit different. It does round off to 12.5916, but it's not that long of a number. We'll write the whole thing down, 59159. Okay, so we've got that. We could have found it a slightly different way, and this is the thing I want to remind you of. If it's been a while since you've used these distribution functions in R. If you had the alpha value alone and you wanted to find the same thing, if I go in and I plug in q chi-square of 0.05, which is the alpha value, comma 6, it's going to give me the value at the bottom of the curve, which is 1.145476. So it's giving me the value way down bottom. And so that's useful sometimes when if we were finding an interval values where we needed both end pieces, then we would do that. But an alternative way to find the answer that we just got would be to keep this as 0.05 if you plugged in alpha, and then to use the lower dot tail option in there and set it equal to false. In other words, you want the upper tail instead of the lower tail. Put in the wrong number there. It should be 6. It gives us the same value. So you could do that as well. I like the fact that it automatically does the lower tail first, and then if you had to do the opposite end, you could just figure out alpha and plug it in its place to get the lower side. So it works out pretty well that way. Okay, so what does the 12.5916 really represent? What is that value? 12.59, so B equals, I will say, B equals 12.59159 is the 95th percentile or quantile. I like percentile better here because that's quantile makes you think of quarters, right? So that is it. That's it for today. I think I've covered everything I want to cover today. We'll pick up with the next slide in 12 and talk about the other chi-squared version next class and get through that. So we'll talk to you guys later, and I hope y'all are having a great day. Take care, guys.